In our last bit of information about alkenes, we learnt about some of their reactions, combustion and addition. What we're going to look at here are two examples of addition reactions that are quite special, I'd almost say unique to alkenes. They don't happen to alkanes. Alright, so in the hydrocarbons that we're learning about at the moment, these reactions will not happen at all to alkanes, only to alkenes. The first of those so that means it relies on a double bond. By the way, these reactions will happen to alkynes, so triple bonds will also allow this sort of reaction. The first of these is oxidation. I'm going to quickly show you that and show you the sort of compare and contrast the two ways we can do this. So what I've prepared is some acidified potassium permanganate, which is a purpley pink colour, and here I've got cyclohexane. And when I mix the two together, I get two layers and not a lot else. If I do the same reaction with cyclohexene, it's going to be amusing trying to get this up here, rightio, I would expect to get a different reaction. Now it does need a little bit of heat to make it happen, so it may not happen straight away. Same initial observation, but you might already see at the bottom the colour has faded. And it goes a little bit gelatinous actually, like a little bit like jelly, on the interface where the two layers meet. If I had enough oxidizing agent here, so enough of the permanganate, then the layer at the top would actually get smaller and smaller and smaller, because what I'm making is actually water soluble, so it would actually dissolve in this bottom layer. So let's see if I'm actually telling the truth here by adding a fair bit. And possibly not enough for you to see, but I definitely can see the bottom layer is bigger than the top layer now. Okay, so what's happening here is that the double bond is being broken. The permanganate, which is purple, is turning into this ion, which is a very, very faint pink, but our eyes don't notice it in the concentration we've got, so it appears colourless. The double bond breaks and it puts a hydroxide group, or hydroxyl group, as we call it in organic chemistry, on each of those carbons that did have the double bond. So I don't have to worry about Markov-Nikov's rule, because the same thing's going on each carbon. So there's no rich get rich or anything like that. It makes what's called a diol, an alcohol with two alcohol functional groups on it. You'll see that it's no longer got a double bond anymore, so therefore it's gone from being an ENE to an ANE. So the name of this is 1,2-cyclohexanediol. Complicated name, isn't it? If it was a smaller molecule, a less complicated molecule, one we've met before maybe, they're a bit easier to name. So I'm going to give you one that we're going to use shortly, which is ethene. Alright, this one here. If I was to do the same reaction to this, sorry, I forgot the acidifying, then this here will turn into this. I'm just using another colour just so you can see what's being added. Remember, it's an addition reaction as well as being oxidation. It's an example of an addition reaction. What's being added? The two OHs. Now for naming this, it's quite tricky, but we go, alright, it's an alcohol, so it's got to end in OL. When we do alcohols, this will become more familiar to you. So the name ends in OL because of that. How many alcohol groups are there? If it was one, I'd just leave it as OL at the end. If there's two of them, it's diol. If there's three of them, it's called triol. You don't go beyond three this year. Okay, so it's a diol. Then I go, how many carbons are in the biggest chain? There's two. And are there any, and how are they bound together? Single bond. So it's an ethane, ethanediol. Then I need to say where those ol groups are. They're on carbon 1 and 2. If they're both on the same, it would be 1,1 ethanediol, but because they're on different carbons, it's 1,2 ethanediol. If you forgot that E, no one will mark you wrong for it, by the way. If you just called it 1,2 ethanediol, would accept that. Alright, but basically it's an ethane with a diol, two alcohol groups tagged on it. They're on different carbons, so say it's 1,2. If they're on the same carbon, it'd be 1,1. Okay. So that's oxidation. That's the first of our other reactions we need to know. Again, reminding you it's an example of an addition, but if you do see permanganate being used, the answer the examiner is really looking for to show that you fully understand is oxidation. Okay. When we've done the oxidation internal, this will make more sense to you as well, because you'll understand what oxidizing agents are. You go, oh, that's one of the most common ones, permanganate. It's one of the strongest ones too. Okay, the other reaction that we are going to look at is polymerisation. This is a really, really useful one. These are what we call addition polymers. See a bit of a trend here with these alkenes. That word addition keeps coming up. So addition polymers are ones where you are adding monomers together. So if I've got this molecule here, which is ethene, we've just said, I can use this to make a polymer called polythene or polyethene. You've probably seen it called polythene, which is a type of plastic. These are the oil-based plastics, the ones that eventually we're going to find other things to use instead, because we're going to run out of oil, so we're going to run out of the chemicals to make these plastics and these other things. One other one that you might have, oh sorry, I'm missing something here. To make this happen, you need lots and lots and lots of ethene molecules. That's quite easy to do. You need heat and you need a polymerizing agent. Something like iron is often used for this. It really is acting like a catalyst. Okay? It breaks the double bond, putting an electron at each side. That allows it to then interact with another one of these molecules and break its double bond and create a single bond in here. Then it'll have a lone electron at the end here and a lone electron at the end here. It comes next to another one, breaks it open and forms a new single bond and so on. What I can't see in this one, because I've used ethene, is it's got a repeating unit. But I'll show you what it is anyway. The repeating unit is basically what this bit here is. And I can see, when I do another one, I'll do polyvinyl chloride for you in a minute, that the same thing is repeating itself over and over. So I can actually show that by putting a square bracket around the first of my repeating units. I put a little n there, which means a huge number. There are huge numbers of this repeating unit in here. I know that because I know what I started with, had only 2 carbons in it. Okay. Now to show you another one, because they're not going to be that easy. If I have chloroethene, which is one with a chlorine on it, chloroethene, it's also got the common name of vinyl chloride. If I heat it and I use a polymerizing agent, it will break the double bond. So I'm going to draw this out with the carbons next to each other. And I'm going to put those things on the top and the bottom. So H for the H2, H and Cl for what we've got here. Then I'm going to break the double bond and put a dot on each side. That's an electron, 1 electron from each one. This is what we call a free radical, actually. Okay, this is going to go on and react with lots and lots and lots of these, ending up with something that looks like this. My habit is to draw 6 carbons. Okay, that's showing 6 of these being involved. And I just copy this below. So I go now you might see the repeating unit is a bit easier to see. HCl, HCl. Can you see a bit of a pattern happening there? Every second carbon has got something different on it. This is the pattern you will see with addition polymers. Every second carbon has something different on it. Now it might be at the top, it might be at the bottom, it might be a mixture of top and bottom. Because being a single bond, these can freely rotate. So sometimes the examiner might trick you by having it there, then the other chlorine there, then the other chlorine there. Don't be fooled. It's the same thing. Okay, they've just rotated this one to put it at the top. Still the same molecule. This, by the way, is called polyvinyl chloride. polyvinyl chloride. I'm sure most of you have met this chemical PVC before somewhere in your life. Okay, it can be used for fabrics, it's plastic, it's used for lots of things. All right. The last one I'll throw in your direction, as it were, sorry, I do it in a different colour so it doesn't get too messy down the bottom, is the sort of thing that if they give you more than one carbon. And what do you do then? So often you'll see this, and you go, oh, how do I do that? Treat the CH3 just like I did with the Cl there. Put it down here. Okay, so if I was to draw this one after polymerization, I'll just show two of the repeating units there. See how I just moved that one down the bottom like I did with the chlorine here? So if you're given one that's got more than one carbon, don't freak out. Draw it the same way as we did here and here. With the double bond broken up, two things above, two things below, and that'll help you work out what it is. Okay. The skills you need to be able to, given a monomer, which is the starting unit, you have to be able to draw a section of the polymer, usually showing 3 repeating units, so 6 carbons in the middle of it. You also need to be able to look at a polymer and go, well, if I can identify the repeating unit, I can go back the other way to work out what the monomer was. Keeping in mind that, of course, it's going to look exactly the same, but instead of a single bond there, it's going to have a double bond. And so those are our last 2 examples of reactions of alkenes. Oxidation, which is very special to alkenes and alkynes, when we're looking at hydrocarbons, and addition polymerization, which is very unique to alkenes and alkynes as well.